Hello everyone and welcome back to another video from the MoBiochem Research Group. In today's video, we're going to talk about one of our most recently published works, which regards the choice of a proper CASSCF active space whenever performing quantum mechanical calculations considering ensembles of geometries. So if we wanted to perform, say, the simulation of the absorption spectrum of a molecule, well, the first thing we would do is to take the equilibrium geometry of the molecule and then perform a quantum mechanical calculation on top of it. However, in real life, molecules undergo vibrational motion, and so we would need to take into account this motion. We could do that, for example, by performing some kind of sampling, such as molecular dynamics, or Wigner, or Monte Carlo, whatever. And then we would perform again a quantum mechanical calculation, this time on top of each one of the sampled geometries. In this way, we would obtain a better approximation of the simulated absorption spectrum. Within the framework of a CASSCF quantum mechanical calculation, we would first of all consider the entire ensemble of molecular orbitals of our system. Then we would subdivide it into three different subspaces as shown here. Within this framework, we would allow for electronic excitations exclusively within the active orbital subspace. Now, if we translate this philosophy into our ensemble of geometries, we would see that in some cases, the active space is preserved. However, for some of the geometries like 2 and 3, we would see that there are some intruder molecular orbitals within the active spaces. In this case, if we want to consider a proper description of the system, we will need to correct all the corresponding active spaces here. So, how do we perform these corrections? Well, the algorithm we have recently proposed to perform this task goes as follows. First of all, we choose a reference molecular orbital space. Then, for each one of the orbitals of the problematic geometry, we compute its overlap integral with each one of the reference orbitals. Then we will do the same thing with the remaining orbitals of the sampled geometry. In this way, we will obtain the so-called overlap matrix between the two orbital spaces. Notice that here we're using in reality the absolute values of the matrix elements. Notice also that each one of the columns in reality represents each one of the sampled molecular orbitals. Afterwards, the algorithm analyzes each one of the columns and determines the corresponding maximum values. This way, we will know which reference molecular orbital is the most affine to each one of the sampled orbitals. So we are going to use this information to label all the sampled molecular orbitals in such a way to know what will be the fate of each one of the orbitals and whether they have to be modified to correct the active space. So the labeling of each one of the sampled molecular orbitals will proceed as follows. In reality, we will have every single matrix element of the overlap matrix having a specific label depending on its position. So the labels we have here are I for ignore, K for keep, R for remove, and A for add. Now, the label that will correspond to each one of the orbitals here clearly will be determined by the position of the maximum value of each column. So, for example, in the case of 1', we will have the label I, which stands for ignore. That is, we're not going to change this orbital or swap it in any way. In a similar manner, we have molecular orbitals 2' and 3', to which correspond the labels K and K again, which stand for keep. So this is similar to the ignore thing, except that in this case they belong to the active space, and the label K means that they will have to be kept within the active space. Now, the really interesting thing happens with orbitals 4' and 5'. Now, it is pretty much intuitive here from just visualizing the orbitals that these two orbitals are not in the right positions. So if you had a larger system, we would in any case need to keep track of all the orbitals that would need to be removed, like in the case of 4', or added, like in the case of 5'. This will be done by constructing the two lists LREM and LAD as shown above. Obviously, LREM stands for all the orbitals that need to be removed from the active space, and LAD for those that need to be added to the active space. So in our case, as we can already see, the 4' orbital will go to the LREM list, whereas the 5' orbital will go to the LAD list. At this point, it is rather straightforward what needs to be done to correct the active space. Namely, we will need to swap the two positions of the two orbitals and then perform a new CASSCF optimization. So the analysis we have just seen goes smoothly for most of the cases. However, since in that case we perform an analysis of one column independently of the other columns, we could have some pathological cases that need to be accounted for. One such example is shown here in this let's see, overlap matrix. So in this case, we have two molecular orbitals that need to be added to the active space, namely 1 and 5. However, they both are affine to the same reference molecular orbital, namely 2. If we assume a one-to-one correspondence between the two orbital spaces, it is clear that this situation need not happen. The second problem here, which stems from the same one-to-one assumption, is that the list of orbitals to be added has more elements than the list of orbitals to be removed. These two lists in reality need to have the same length. Okay, so before going ahead and seeing how we tackle each one of these problematic situations, first of all, let's take a closer look to the structure of the overlap matrix with the corresponding labels. So let us first, let's say, subdivide it into different sections so that we evidence the active spaces of the sampled and of the reference orbitals. Okay, that's better. Now, let us first take a look at what is in the center. So let's say the Cartesian product of these two sets. Well, we see that in all cases we have the same label, namely keep. This is because if the orbital happens to be here and is affine to a reference orbital, well, we don't need to modify it. Okay, so now let's see what happens here to the sides. So, for example, in the case of 1' and 5', or whatever would happen to the left and to the right if we had a larger set, well, we have these sections labeled with the A, which stands for at the orbital space. Now, in the four corners, instead, we have these labels, I, so we ignore, so the orbitals would need to be ignored. And instead, in these two sections, above and below the active space here, these orbitals would need to be removed since they would be affine to orbitals outside of the reference active space. Okay, now let's go ahead. Okay, so now let's go back to the pathological situation we had evidenced before. So in this case, as we had seen before, well, we have the situation in which we would like to add both 1 and 5 to the active space, but only 4' would need to be removed. So how does the algorithm proceed? Well, in reality, it analyzes each one of the columns separately. However, whenever it faces a situation like this one here, it will immediately compare the two implicated matrix elements. That is to say, it will see which one is the larger one and which one is the smaller one. Now, in this situation, we have that the matrix element 2, 5' is the smaller one. In this case, the algorithm will automatically remove the label add to this orbital, and accordingly, it would update the LAD list. Here we have solved both problems, since now we also have LAD having the same length as LREM. Of course, it would proceed in an analogous manner if we had the opposite situation here. So in this case, it would instead eliminate the orbital 1' from the LAD list, as shown here. Now, one important thing to know here is that the algorithm performs this analysis on the fly, that is, as it is performing the analysis of each one of the columns. However, it could also happen that after the analysis of the columns has finished, you could still have the situation in which these two lists do not need to have the same length. Now, to tackle this problem, this time the algorithm, or let's say the second part of the algorithm, which we will now call row analysis, well, as its name suggests, will analyze the rows of the overlap matrix. Now, here we have to consider case by case what happens depending on the situation. But broadly speaking, we will have 4 different cases. So 2 cases in the case of in which LAT has less elements than LRAM, and 2 other cases in the opposite situation. So let's start with this situation here. Okay, so if we face one such situation after the column-wise analysis, we will perform the so-called row-wise analysis, or simply row analysis. In this case, we're going to analyze each one of the rows exclusively corresponding to reference molecular orbitals. So specifically, we're going to determine basically the maximum value of each one of the rows. Now, what do we see here? We see that in the case of row 4, its maximum corresponds to a sampled orbital which is outside of the active space. This basically suggests that although on the basis of the column-wise analysis this orbital would have to be ignored, in reality this is suggesting that we should add this orbital in the active space. Okay, so in this case we update, let's say, its label and update the corresponding LAT list with the 1' orbital. In this way, we have solved the problem of the lengths of the 2 lists, and now we have a one-to-one correspondence. Okay, so now let us analyze case 2 of the same situation we had seen before. So let us perform the row-wise analysis and see what happens. Well, in this case, specifically, if we take a look at row 3, we see that its maximum value happens to be precisely at a place of 4'. However, according to the column-wise analysis, 4' was one orbital that needed to be removed from the active space. Noteworthy, the row-wise analysis indicates that in reality 4' has also a strong contribution from a reference orbital, and thus it would rather be wise to keep it within the active space instead of removing it. So this is exactly what the algorithm does. So it changes the status of 4' from R to K, and it updates the corresponding LRAM list. Okay, so now let's see what happens in the opposite situation. That is, one in which the number of orbitals to add to the active space is greater than the number of orbitals to be removed. So let's perform the row-wise analysis and see what happens. Well, first of all, the conflicting orbitals here are 1' and 5'. Now let's take a look at the corresponding column maxima. Well, in the case of 1', we see that the column maximum is this element here. However, the row maximum of the corresponding row is this element here, which is inside the sampled active space. That is the same as saying that perhaps 1' is not the orbital that is most similar to orbital 3 from the reference space. Thus, perhaps it wouldn't be wise to put this orbital within the active space. On the other hand, if we see 5', we can evidence that the column maximum here also corresponds to the row maximum. Thus, the algorithm proceeds by eliminating 1' from the, let's say, add orbital list, as also shown down here. And now we have the same number of orbitals in these 2 lists. Okay, so let us now see what could happen in another possibility of this case here. So here we have one orbital in the LAT list and non-orbital in the LRAM list. So we perform again the row-wise analysis, and in this case we see that, well, in particular for this 4' orbital within the sample active space, we see that its column maximum is here, but it does not correspond to the row maximum Instead, the row maximum corresponds to an orbital which is outside of the active space. Thus, this indicates that actually this orbital 4' should not be kept within the active space, because it might have contributions from orbitals outside of the active space. So instead, we relabel it as a remove orbital and update this LREM list. And so at this point, we have the two lists having the same length. Okay, so now let us examine the efficacy of the algorithm presented above. So in our study, we have considered all 5 nucleobases, and for each nucleobase, we have performed a 100 nanosecond molecular dynamic simulation in water. For each of these simulations, we have sampled 100 geometries, and for every geometry, we have performed a CASSCF calculation in 2 situations. First, in vacuum, that is, without the point charges of the surrounding environment, and second, in water, that is, with the point charges of the environment. Okay, in this diagram, we are showing both the situations together, but first, let us examine the vacuum case. So, the success rate for the recovered geometries is shown in these percentages. As we can see, we get a 100% of success rate for almost all nucleobases, and yet an 87% in the case of guanine, which nonetheless is still a good percentage. Now, if we go from vacuum to water, we see that in most cases, the number of geometries recovered is lower than the overall number of wrong geometries. This is particularly true in the case of guanine, for which we have a 74% of success rate. It is actually interesting to see that the number of recovered geometries when we consider the surrounding environment is lower with respect to the case in which we consider the geometries in vacuum. Now, if we take a closer look to the molecular orbitals of the geometries for which the active spaces were not corrected, we can see that in all cases, these orbitals correspond to lone pair orbitals. Now, at this point, we could hypothesize that these orbitals are more exposed to the surrounding environment and thus are proner to somehow change their energetics depending on the presence or absence of some point charges. However, at this point, it is still object of study in our group, and we will present the results in the future. So stay tuned to know the answer. Okay, so now that we have examined the efficacy of our algorithm, it is time to provide it a motivation. Why do we even bother in performing the correction of the active spaces of different geometries? Well, first of all, the CASSCF method is a variational one. This means that the lower the energy of the approximate wave function, the better the description of our system. Now, in our case, we have observed that for most of our geometries, the energies of the corrected wave functions are lower than the uncorrected counterparts. Now, these energy differences also reflect themselves upon different observables. One example is the density of states of uracil in this case, which dramatically changes from the uncorrected geometries to the corrected counterparts. Now, this lowering in energy when considering CASPT2 calculations on top of the previous CASSCF calculations is not observed. The main reason is because CASPT2 is not a variational method. Thus, in this case, you could obtain similar line shapes for observables obtained using the uncorrected active space and a corrected counterpart. However, the nature of the underlying wave functions will strongly be different. Therefore, it is strongly advisable to correct the active space, even when performing CASPT2 calculations. So, to summarize, we have proposed an algorithm that allows for correcting the active space of an ensemble of geometries, which relies on a calculation of the overlap matrix. In particular, relies on the analysis of the row and a column maxima of this matrix. Now, we have seen that solvent might be associated with the difficulty of recovering the active space, since in the case of the same geometries in vacuum, we can recover more geometries. And finally, it is strongly advisable to correct the active space, as we have observed in the case of CASSCF. The reason is because it is variational and we obtain a better description of the system. And with this, I would like to thank you all for your kind attention. If you have any questions or suggestions on how to improve our algorithm, please put it in the comments. If you enjoyed the video, don't forget to put a like and subscribe to our Mo Biochem channel. Stay safe and enjoy the holidays. Thank you.